All right, we are into our second week of graph theory. Last time we talked about the Euler characteristic, which the Euler characteristic says that if we take the number of vertices, subtract the number of edges, and add the number of faces for any planar graph, then that has to equal 2. And one important caveat here is that when we're counting our faces, we want to include all of the interior faces, but we also want to count the outside piece as a face as well. So a few of you had questions as to why we bother counting this outside part as a face, and why don't we just sort of adjust what our Euler characteristic is supposed to be to accommodate this. A main reason that we choose to define it this way is that it allows us to write or draw our graphs on a variety of different surfaces in a consistent way. All right, here's what I mean by that. Let's say rather than drawing a graph like this one on a sheet of paper on some flat two-dimensional plane, let's draw it on a sphere. So we could imagine a spherical chalkboard, or you could go outside, take a piece of chalk, and draw something like this on the ground, and because we are on the surface of a sphere, this outside piece is really also just a face. It's just the face of the Earth that is everything except for what you've drawn inside of this square. So when we count our faces, it makes sense to count this outside one. It's really no different than the others, other than maybe being significantly larger, but we don't really care about that type of difference. So we can say that if we draw a graph on a plane, the Euler characteristic must be equal to 2, and that the same thing holds if we draw on the surface of a sphere. We would still have an Euler characteristic equaling 2. These are really sort of, for our intents and purposes, these are really essentially the same thing. However, today we're talking about other surfaces that end up having different Euler characteristics and actually allow us to draw different graphs that don't have crossings on them, as we'll see in a little bit. All right, so we're talking about surfaces. So here are a few common examples. First up is the XY plane. So if we take our traditional two-dimensional flat plane that goes off forever in all directions, that's a great example of a surface. Another fundamentally different surface is the sphere. And on a small scale, so zoomed way in, there's really no difference between a plane and a sphere. Right? It's sort of natural to think that the world is flat because when you look around, everything seems flat to you. It's not until you get to the big, broad scale, it's not until you zoom out to a bigger scale that you see some actual difference. On the global scale, if we travel in a direction long enough, we'll end up back where we start. That's not true on a flat plane. Right? So a plane and a sphere are fundamentally different because there are some global properties that distinguish them. Right. Yet another example of a surface would be a torus. So a torus is the surface or the boundary of a donut. Right. So we don't care about what's inside of this. When we talk about a sphere, we're talking about the outside piece. We're not talking about the inside. Same thing with a torus. We're only talking about the surface of this shape. But you can see that this torus is different than a sphere. There are a few ways of pointing out the fundamental differences between a torus and a sphere. A lot of them have to do with keeping track of paths that we can walk around and end up back where we start. So a torus has several sort of fundamentally different routes. We can go around this way, and separately we could instead go around this way. Whereas with the sphere, routes aren't necessarily fundamentally different. If you're curious about that distinction at all, please let me know. I will talk for forever about these types of geometric ideas. But we don't really need to get into them now. So here's my claim. I claim that the Euler characteristic, this vertices minus edges plus faces calculation that we do, that we saw last time is always equal to 2 for a planar graph, that this Euler characteristic is equal to 2 for planes and for spheres, but is something different, actually ends up being equal to 0 when we're working with a surface like a torus. And in fact, for other surfaces that we'll get to later on, we can have even different Euler characteristics. To see this, let's talk about another way of thinking about a torus, of drawing a torus. One really nice thing about something like the xy plane is that we can draw it on a flat sheet of paper. Right? The whole point of things like a map of the world is that it takes a sphere, it takes an inherently difficult to look at object and flattens it out, makes it so that we can have it on a sheet of paper or on a computer screen. One issue with a lot of projections or ways of doing that is that it distorts the picture in some way. Yeah. So what we're after is a way of taking the torus and making it flat without introducing some sort of distortion. And we can actually do that for a torus using this following construction. The way we'll do that is we'll start with a square or a rectangle, and we're going to identify opposite edges. So I've drawn it with orange edges and blue edges. And I've drawn arrows on them just so we know how to keep things straight. The idea is that we'll take this rectangle and we will deform it through three-dimensional space so that we can identify opposite edges to each other. So here is a nice handy rectangle. Here's a sheet of paper. The idea is that we want to identify the left edge to the right edge. And one way to do that is to take it and fold it so that we have a cylinder. So if we take a rectangle and we glue the left and right edges to each other, what we're left with is a cylinder. We want to do this again for the blue edges. And when we do that, we end up with a torus. I'm not going to try to do that with a piece of paper because it gets crumpled and doesn't look very good. But here is an animation that shows this interpretation. So these two steps tell us how we can get from something like a square or a rectangle to a torus. And we can reverse this process as well. If we have a normal torus, we can break it up into pieces. We can cut it open along something like this blue and something like this orange edges to reverse the process and get back to a square. So the idea is that we can use a representation like this to represent what's actually happening on the torus. I like to think of this as having the Pac-Man rule. So in classic Pac-Man, if you go off one edge, you sort of magically appear on the other side. So one interpretation is that there's some teleporter that sends you to the other side, but another way of thinking about that is that rather than playing on a flat plane, maybe the entire game is happening on a cylinder, and when you go off of the left side, you're actually really just wrapping around the back side of the cylinder. All right. So same idea, if we are a person who is standing on this torus and we pass this barrier, right? This line doesn't actually mean anything, maybe it doesn't even really exist, but we appear over on the other side. And the same thing happens if we go off of the top, we end up coming out of the bottom here. This isn't actually any significant change. We don't feel like we're like jumping through space or anything. Really, this just amounts to walking around on the surface of a torus like this, and all we're doing is crossing this imaginary barrier, this imaginary line. So we can go for a walk, we can travel around over here on this torus, and what that amounts to, whenever we cross one of these lines, we just sort of appear on the other side. So a path might look something like this, which looks broken up in our picture. However, that's just a perfectly normal trip to take over here on our torus. All right, now let's say that I want to know what the Euler characteristic, v minus e plus f, of a graph that's drawn on a torus, what that looks like. And this time, we have to be especially careful with what we mean by a face. Okay. So here is a graph. We have K3, the complete graph on 3 vertices, drawn on the surface of a torus. And if we did the Euler characteristic calculation for this, we would see that we have 3 vertices, we would have 3 edges, and then we would have at least one face. We would have this triangular face on the inside here, but what happens on the outside? And at this point, we're actually rescinding the let's just count the outside as a face rule, because the outside part of this graph, so everything outside of this triangle, actually looks pretty different than every other face that we've worked with before. Normally a face is kind of similar to a flat disk. Maybe it's in the shape of a triangle or a square or some other shape, but it's sort of fundamentally that flat piece. In this case, everything outside of this triangle has this whole handle to it, right? So that actually doesn't count as a face. We want to, when we're doing this calculation, look at a graph that splits up those weird face pieces. Right, so let's do another example. Right, so here is a graph that is drawn on the surface of a torus. We have the same, so the torus, yeah. So here is a graph that is drawn on the surface of a torus. This black piece is representing the torus itself, and we have our blue vertex and our orange edges. Notice that this graph is not simple. We've got an edge that leaves a vertex and comes back to that same vertex. We actually have two edges that have this property, but the Euler characteristic calculation works even for graphs that aren't simple. All right, so let's calculate what the Euler characteristic is here. How many edges, how many vertices, and how many faces do we have? Well, we only really have one vertex. We have two edges, so I would say that the one that goes around the torus the short way and one that goes around the long way are two separate edges. And now I claim that there is one face. And this is a little bit more difficult to see, but this, the face, the only face, is the same thing as the square in our turning a square into a torus construction. So if there is one face, then vertices minus edges plus faces equals 0. And this ends up being the Euler characteristic that we will always get when finding the Euler characteristic for a graph that is drawn on a torus, provided that we are treating faces the right way, that no face has some weird handle on it. We have edges that sort of cut through all of the regions or all of the parts of the torus. Apologies for the very hand-wavy definitions there, but it's not worth getting into too much more detail than that. So one of the main reasons that we bothered with this turning a square into a torus construction was that for a lot of other graphs, it's easier to work with the torus in its unfolded picture. So here I've taken the same graph and I've unfolded it into our square. And so rather than one blue vertex, I've drawn it where there are many such vertices. But we're adding in the rule that we are gluing opposite edges to each other. And so now I'm labeling these with black arrows. The single arrows get glued to each other. The double arrows get glued to each other. Okay. So this picture looks like it has 4 vertices, but actually when we do this gluing, this vertex gets glued to this other vertex. All of these end up really just being different pictures of that same single vertex that we have over here. Right. Similarly, it looks like we have 4 edges, but when we glue the left and right edges to each other, we're basically saying that they're the same thing, so they only count as one edge. So we have to be a little bit careful with how we count vertices and edges when working with the unfolded picture, but this can be helpful. This can be an easier way of drawing these where we don't have to try to be drawing on the surface of something that's curved, which can be a tricky thing to do. Either way, when we're drawing on a torus, the Euler characteristic for the graph should always be equal to 0. In fact, because this is a fundamental property of the surface itself, we typically say that the surface has an Euler characteristic of whatever its graph supports. In this first graph on a torus, we had edges running along the sides that made up the square that formed the torus, which actually ends up being something that we won't usually do. More typically, we'll have a picture like this one, where the square that gets folded up into a torus really is completely independent of the edges and vertices. So here's an example. Here are 3 vertices, and if I want to draw edges connecting them, I can draw them entirely contained in the square. That's perfectly legal to do. Maybe there's that edge, maybe there's this edge. But maybe this point here is connected to this other point through an edge that goes off the other direction. So we have an edge that looks more like this. So this edge looks strange, like it's broken up into multiple pieces, but remember we have the rule that this point is glued onto this point. This whole edge is folded through space to be glued over to this other edge, right? It's the Pac-Man rule. If we go off this way, we end up over here. So this is a perfectly valid edge. We could also have a slightly stranger path. Maybe if we went this way, well, once we go off the left side, we come over on the right side. And then maybe if we keep going, once we go off the top, we come out the bottom, and then maybe we are over here. So this would be not a simple graph because we have multiple edges that connect the same two vertices, but I'm just illustrating a point here that we can draw a graph using sort of this style of picture. Why do we care about any of these surfaces? Well, last time we started talking about the Euler characteristic in the context of proving that K5 was not planar. It's not possible to draw this graph on a flat plane where the edges don't cross each other. The proof of this hinged on the fact that for a planar graph, vertices minus edges plus faces has to equal 2. So for a graph like K5 that has 5 vertices, a total of 10 edges, well, then it better be the case that f, our number of faces, equals 7. Separately, last time we showed that if we count up the number of faces and we count up the number of edges, it better be the case that 3 times the number of faces is less than or equal to 2 times the number of edges. In other words, the number of edges that we have puts an upper limit on the number of faces that we're allowed. Well, if our edge count is 10, then we run into trouble because our planar graph K5 wants there to be 7 faces, but 21 is not less than 20, so we've gone over our limits. We have too many faces required in order to build this planar graph. We want to have more space in which to draw this graph than we actually do in a plane. Right? This is where other surfaces come in. It's not possible to draw K5 on a plane, but if our Euler characteristic was allowed to be something different, like 0, that changes our expectation for the number of faces that we need. In other words, we just might be able to draw a graph like K5 on a different surface, like a torus. I'll be leaving most of the details for this up to you and your groups, but at some point I will share out plenty of images of graphs on different surfaces.